Hey everyone! So this is the last video in the set of lessons on recursion, and we're going to be talking about recursive processes in this one. Alright, so this first code example that we're going to look at together is this jump function. And so I just want you to take a second to yourself, maybe pause the video and think what looks different in this function than what looks different here compared to functions that you've seen in the past in the course up to this point. All right, assuming you took a second to pause and think to yourself, lines 5 and 8 should have stood out to you. And so as we've discussed in the previous two videos, something's recursive if it's defined in terms of itself. And so when we talk about defining functions, we're talking about steps of an algorithm or steps of a process, right? And so the function body, lines 2 through 9, are the instructions that we're telling the computer to execute each time the jump function is called. And so on lines 5 and 8, when we have some, you can imagine some jump frame is open on the stack, when we hit line 5 or line 8, we're getting interrupted and adding a new jump frame and opening that up in the middle of our execution of a previous jump frame. So knowing that, why don't we just go ahead and see if we can't step through an evaluation of a jump function call given the tools that we've already built up in our repertoire thus far in the semester. So let's see if we can handle this. So I'm going to go ahead and switch into another tab so we can diagram this together. So let's do that. So I'm going to say we diagram this with, assuming that this was called with the arguments 5 and 4. Alright, so let's set up our diagram with the stack and the heap. Alright, and so we're going to see if we can make it through this recursive function call diagram, knowing everything that we have learned up to this point, and nothing else. So hopefully this will convince you all that you have learned so much. You should be so proud of yourselves. It's been a rough semester, I'm sure, for everybody, but you should walk away feeling proud that you have come out of this class with some incredible, powerful knowledge. So let's first add the globals frame, as always, and so I'm just going to assume that this function call was made on line 11. Okay, and so the jump function is defined at the global level on lines 1 through 9. Okay, and so we call jump, and our return address is 11, and our low parameter is 5, and our high is 4. Okay, so the first if statement is checking, is our low equal to our high? It is not. So on line 4, the second condition is the low greater than the high. This is true. And so we enter this block on right here. So hopefully you can see this. And so on line 5, we create a local variable around that is going to hold the result of calling jump again. So right here, I'm going to create put a little star, if I can make it a little bit smaller. So right here, I'm leaving a bookmark because we're getting interrupted. On line 5, we're calling jump in the middle of executing a jump frame. And so just like any other diagram, when we call a function within a function, right, we just pause what we're doing and just go add another frame. This is no different, right? we do the exact same thing. It just happens to be that it's the exact same function. And so it just becomes a bit more confusing to trace. That's it. Okay, so you just continue on like you would any other diagram. And so now we have a function call, or a function call frame with the same name but a different return address. So we were called from line 5 this time. Our high and our low were, let's be a little bit careful about this, right? So notice that the low argument, or the low parameter here, was 5, right? But 5 is actually sorry, I'm not being clear here, but so low is the first parameter, which was what 5 was assigned to when we called this function initially. But right here, when we call this jump function again, the first argument we give is high, which is what 4 is. So that means when we're setting up the parameters in this second frame, they are swapped, right? So let me set that up. And let me use a different color to just make this extra clear what just happened. So when we call this jump function recursively on line 5, the order of our parameters, we just swapped them there. Okay, because our low parameter was indeed greater than our high, so we just swapped them when we called it recursively on line 5. Right, and so that's reflected on in this second frame. Okay, and let me delete those arrows. Okay, so let's continue on with this second jump frame. All right, so now we're in a second jump frame where we start from the top and we check, is this low 4 equal to the high? It is not. And so we continue on to line 4 where we check, is 4 greater than the high? It's not. So now in the second frame, we enter the else block where we create a local variable up that is the result of calling jump recursively again. So we're interrupted a third time. Okay? So we have another recursive call. A function call is a recursive call if we're calling itself. That's a vocab term you'll hear me repeat, and we'll really drill that in today. So on line 8, we call jump again. And so anytime we have a function call within a function, we always add another frame. That's nothing new. And so let's add another frame here. So we called jump again from line 8. But now, what were our arguments? Our arguments were low plus 1. So our low in the previous frame, it was 4. So that means the low here is now 5, and high was unmodified. So this is where we are in this third jump frame. So we start from the beginning of the jump function definition on line 2, and now we're on line 2, and we check, is low equal to high? In this case, this is indeed true, and so we return low, which is 5. Okay, so now this recursion is terminating. We are no longer calling ourselves. And so remember, this is what we want. We always want to be working towards the case where our recursion stops. Okay, so the recursion stops, the RV, we hit this return statement 5. And where are we returning it to? We're returning it to line 8. and we're looking in our code listing, line 8 is here where this star was. Okay, this star was where this up variable was created. Okay, and so when you're figuring out where to return values back to with nested function calls and function calls within function calls, it's a lot easier to trace back when the functions are different, right? When you're not tracing a recursive function call. The rule of thumb when resolving these recursive diagrams is you want to just look at what is the most recently opened frame on my stack that has not yet returned. And you can figure that out by checking on your stack what is the lowest frame that doesn't have a return value yet. And so here, my lowest jump frame that doesn't have a return value is right here, right? There's no RV here, so that means we're not done yet. And so this matches up, right? Because my RA was line 8, and right here, there's this up variable where on line 8 that needed this value to be filled in, 5. Okay, great. And so that is resolved. Line 8 is finally resolved. And so we can finally, this bookmark can finally be removed, right? Because when we were executing this second jump frame, that's why we put this star here. We put this star here when we had to go resolve that recursive jump call. Okay, so but now we resolved it. This third frame is done, and we figured out what the value for up is, so we can delete this star. We figured that out, and now we can resolve the remainder of this second frame and fill in or execute line 9, which is just returning low plus up. And so low is 4, up is 5, and so 4 plus 5 is 9. So we're returning 9. And where are we returning that to? We're returning that to line 5. That's a return address. Oops, and I'm sorry, I thought I deleted that bookmark, but I guess it came back. Okay, sorry. Great. Yeah, so we return that to line 5, which is up here in this final jump frame, filling in for the around variable. Okay, and that means we can finally get rid of this last remaining bookmark, right? We were just waiting for this last jump frame to return, so we can get rid of that. Okay, and now the final line that needs to be executed is line 6, which returns around. Okay, and I apologize, that should have been 9, not 5. My mistake, right? Because the return value here is 9, and that's what gets filled in here. And we return around, which is also 9, and that completes this diagram. All right. So this is an example of a recursive function that is calling itself. And so here, this function call expression, jump 5, 4, results in 3 frames on the stack, all to the same function, right? Jump 5, 4 results in 3 calls to the jump function. If we had done jump 5, 5, this would have just resulted in a single call to the jump function, right? Because we just would have right off the bat just let me change the color here. Right off the bat, we would have hit this case where the low and the high are equal and just return the low. And we would have never had to resolve any recursion. All right, and so here, while it may have been a little bit mind-bending, I definitely recommend working through this example again if you had some trouble, which is totally normal. Take your time and work through this again, and feel free to shoot me an email if anything was confusing. But despite, so totally normal if any of that was a bit tricky, but I hope you can see that there's nothing like mysterious happening here. We were able to just use the tools that we've been building up in our toolbox up to this point in the semester to evaluate this code listing like a computer would. All right, so let's summarize what we just learned back in the slides. So there's just a few vocab terms that I want to cover and summarize. So first is the base case. So a base case in a recursive function, or recursive process. So we talked about in the recursive structures video how a base case there is how we terminate a recursive structure or stop it from like requiring infinitely more objects to be constructed. A base case here is what stops execution. So it's a conditional branch that does not result in a recursive function call. So in that example we just traced through, it was the case where the low and the high were equal and we just returned the low. Okay, so that's the base case. A recursive case is a branch that does result in a recursive function call. Okay, and so in the example we just did, we had two recursive cases, right? We had the case where the low was greater than the high, and then we had the other case where that was not the case. That was not true, right? All right, and then we also have the recursive call, which is actually when the function is calling itself. And so each recursive call should bring the evaluation closer to reaching the base case. And so what do I mean, bring the evaluation closer to reaching the base case? So I'm going to just quickly go back to our slides here. Let me clear some of this really quickly. Actually, yeah, it's fine. So here you can see, like, for example, on line 8, this is the case where the low is less than the high. So on line 8, you only reach that case when the low is less than the high, right? Because if the low is equal to the high, you enter the then block on line 3, right? If the low is greater than the high, you enter the then block starting on line 5. So if you're entering the block starting on line 8, right, the low is less than the high. And so you're moving closer and closer to termination by updating this argument on line 8 by updating low plus 1 in this function call. So what do I mean by this? If you didn't follow what I just said out loud, I'm going to write over to this side. Ooh, wrong color. I'm just going to actually... All right, so back in this code listing, right, we only come to this first, we only enter this first block if the low is equal to the high, right? We only enter this block if the low is greater than the high, and this last block is if the low is less than the high, right? And so what I was just saying is that with the recursive cases, you need to be making progress towards the base case, or else you end up with infinite recursion. And so how are we making progress in this example? I think one of the most common ways you see the progress being made is by an update to the argument. So here, this is the case where the low is greater than the high. And so we make progress towards that base case by calling the function again, but calling it again with a bigger value in the low. So we call it again with our low incremented. And so in the subsequent call to jump, either our low will still be too small or we'll finally hit this base case. Okay, does that make sense? Hopefully. And then so that's how this case is making progress. this case is making progress by swapping these values, right? So in this case, the low is greater than the high, and so if they're not equal at this point, we swap them, and then we can start making progress in this block. Okay, and that's what we saw happen when we traced through. All right, cool. So I'm gonna go to another example. So here is a famous this function is code for computing Fibonacci numbers. So the Fibonacci numbers are famous sequence of numbers. You should look them up, read about it on Wikipedia. It's a famous sequence of numbers that is often used for teaching recursion. But I'm going to use this function to go over some of these vocab terms that we just used. So right here we have this short code listing, and just based on these lines, we should be able to pick out the key elements of the recursion. So the first question we have here is, which lines make up the base case? Okay, and so I encourage you all to pause and try to answer these on your own first before I go through it. But I'll assume you paused and did that, but I'm just going to do it. And so remember, the base case is the case or the branch of control flow that terminates recursion. And so for this example, that would be line 7 through 8, because line 7 through 8 do not result in a recursive call. Line 7 through 8 simply just return the integer that was given as an argument, but lines 4 through 6 are the recursive case, right? Because on lines 5 and 6, we have recursive calls to the f function. And so that kind of answered number 2, which is how many recursive function call expressions are in the recursive case. And the answer there is 2. And so there can be multiple recursive function calls in one branch of like execution, or one control flow branch basically here. Like for example here in this first example, each branch of control flow had its own separate recursive case, or recursive call, I mean. But this lines 5 and 6 could have called jump 6 times each, and that would have been fine. But that would have just been a nightmare to diagram, so that's why we didn't do that. All right. And so, are the recursive calls making progress towards the base case? And so the answer there is true, right? Because we are recursively calling f if x is greater than or equal to 2. And so that means that we hit the base case when that is not true, or when x is less than 2, right? And so if the argument to the recursive case, or the recursive call, is subtracting from the argument, that means we're making progress, right? The base case is going to be hit once this argument is less than 2. So if every recursive call is subtracting, that means we're making progress there. All right? And then the last question is a little bit tricky, so we can work through that together, is without diagramming, how many frames for f are needed to complete the code listing? And the answer is 5, and I can work out my strategy for how I would work through that. You don't need to diagram this to figure out how many recursive calls are needed. You can think of this as a tree, and so trees lend themselves naturally to recursion, and we talked about that briefly in the recursive structures video, but both in nature and in the data structures sense. But yeah, so right here, we call this with f of 3. Okay, and so we call function f with argument 3. And so f of 3 will result in the function being called again with f of x minus 2, which is the same thing as f of 1. Okay, right, because 3 minus 2 is 1, okay? It will also result in f of x minus 1, which is f of 2. Okay. And so now we have to evaluate both f of 1 and f of 2. And so f of 1 is going to hit the base case, right? Because that 1 is less than 2. Okay. But f of 2 does not hit the base case. So f of 2 results in an f of 0, because that is this line, right? And another f of 1, because that is this expression. Okay, and so this tree of function calls is kind of being built, and so you can count these up, and this is 5. So the last thing that I want to do, now that we've done some work with recursive processes together, is tie it back to these recursive structures and show how they can work together. And so I thought we could just write a function together to count up the number of nodes in a linked list. Okay, so let's do that. So below our nice node class, let's write a function together. So let's call it count. And so count is going to take in some list of linked, so it's going to take in a singly linked list, which, remember, is when we're dealing with linked lists, we declare something as that type using this optional node type, which means it can either be a linked list or it can be none. Okay, and it's going to return to us an int, which just counts up the length of a linked list. Okay, and so whenever we're wanting to write a recursive function, we just had some practice tracing through a couple recursive processes. Whenever we're wanting to write one of our own, it's often easiest to start off thinking about it in terms of like the smallest possible case, which is the base case, right? And so with a linked list, the base case is the case when the list is none. So if the list is none, so when the list is none, that means that there's no nodes in our list and the length is 0. So we can just go ahead and return 0. Great, so that is the base case. So otherwise, if the list is not none, that means we have at least something in the list. So we have at least one thing in the list. So that means the head of our linked list is not none. So we have at least something. We have one thing in our list. The head is not none. And so what we can do is we can just let this function recursively calculate the length of the list's next attribute in addition to our self. Right, and we need to remember to return this value. All right, and I'm sorry, this was a bad idea. I'm gonna change this name to be, should use head because list is probably a keyword since it's a built-in data type in Python. Right, okay, so what's happening here? So this is only 4 lines of code, but this is gonna work. Just to reiterate what's happening, if our linked list, if there's nothing there, the length is 0, right? So we return to 0. Otherwise, I know all I'm worried about is myself. I can say, yes, I'm here, and I'm just going to pass the rest of the problem on to the function recursively to go calculate. Okay? And so we can just go ahead and test this out and see what happens. So if we print out the count of a node and run this, let's see, let me just clear this. Yeah, we get 3. Awesome. So this might seem like a little bit of witchcraft, so let's diagram an example together. All right, so definitely feel free to pause the video to catch up to me. I just went ahead and drew out the linked list that results from lines 27 through 29, and I went through in detail in the recursive structures video how to do this. But yeah, feel free to go back and watch that, and if you're feeling confused about how we got here. So let's go ahead and diagram line 30. So we call count on line 30. And so the head, so I'm going to change colors just to make this more clear. So the head is going to refer to a node. And we're going to check, is head none? It is not. So we are going to return 1. So I'm just going to do some keep track of some scratch work on the side. So the first time we called count with a list that was equivalent to 1, 2, and 3, right? And it told, when we hit that return statement, it said to return 1 plus the result of calling count with 2, 3. Okay, and actually it's 2, 3, and none is the full list. Okay, so actually let me just rewrite this to be more precise. And this is just scratch work that I'm drawing. This is just to help make the recursion more clear, similar to that tree that I drew. So this first call to count, 1, 2, 3, none, hits the return statement 1 plus count of 1, or 1 plus count 2. Right, because it's saying return 1 plus count of head.next. Okay, and that makes sense because head's next attribute refers to this sublist. Okay, and the sublist I just circled in red only has nodes with 2 and 3 in the data attributes. Okay, and so I'm going to change colors. Again, we're going to add another frame, and so we call count again, this time from line 24, and now the head is this node, because remember we were called with this head.next right here, and so we check, is this head none? Nope. This is not none, right? This is a full node. And so we enter the else block and we return 1 plus a recursive call, the result of calling this count again, with the argument being the next attribute sent in. Okay, and so that is this sublist. Okay, and so I'll change color again to show that. So we call count again, from 24. Now our head is this last node 3. Our head is still not none. This is a node. This is a full node. So we hit that else statement. That is 1 plus a recursive call to count with our next attribute sent in as that argument. But the next here is none, right? Sorry, I forgot to write that in. But our next attribute of this node on our heap is none. Okay? And so when we call, we have one last recursive call here where we are calling count with none. And so let me just add that to the heap, and I'll just do it in black. So we call count again from line 24. But this time our head is indeed, it is none, okay? And so when the head is none, that means we return 0. Okay? And so when we return 0, we've been sort of building downwards this is not exactly like a recursion tree, but you can sort of think of it in a similar way to that Fibonacci tree that we built in the previous problem. But this 0 is this, we finally hit this base case, so now we can collapse up and compute these additions that we've been kind of procrastinating on. Okay, and so this count of none expression that we set a bookmark in the green frame. So this green count frame we never returned from, right? The line 24 in the green frame never finished. This line 24, 1 plus count of head.next in the green frame, we were waiting on a value from a next recursive call. We got that value in the black frame, it's 0. And so now we can finish off that 1 plus 0 and fill in the RV as 1 in the green frame. Okay? This 1 in the green frame returns back up and replaces the recursive call from the blue frame. Okay? And so line 24 in the blue frame gets added to a 1. Okay? And so 1 plus 1 is 2. Okay, that gets returned back up and replaces the recursive call from within the red frame and added to a 1, which becomes 3, because 2 plus 1 is 3. And so our final return value is 3. We counted up the 3 nodes in this linked list. All right, that was all that I was hoping to make it through for today's lesson. So thank you all for watching, and hope you're sufficiently dazzled by the power of recursion. We're really just scratching the surface here of the cool things that you can do with both recursive processes and recursive structures. And so definitely make sure you come to Tuesday's class to see more. But yeah, thanks for watching.